This lecture is going to be about decision analysis. We are continuing to move away from just modeling and simulating the behavior of dynamic systems in the energy industry, and we're moving towards following our discussion of deterministic optimization, more of a focus on decision making and trying to figure out how we make decisions under uncertainty in dynamic systems. So decision analysis is a formal structure for how to make decisions under uncertainty. And it's a pretty broad field. It includes a wide variety of approaches for making decisions based on multiple criteria. Most of what we're going to talk about today depends on maximizing expected value, right? So if we have a bunch of choices about what to do, and they all lead to different outcomes, we're going to say that the different outcomes are not set in stone, right? Our decisions, the decisions that we make, the consequences can be a little bit uncertain. But our criteria for making decisions based on that uncertainty is to just take the expected value, right? So that another way of saying that is if you had 5 different choices that you could make, and each of those 5 choices gave you a probability distribution, what we're really comparing is the mean, or the expected value of all of those different probability distributions, and that's the criteria we're using to make a decision about which choice is best. So decision analysis often relies on a visual or graphical tool called a decision tree. And this is a pretty straightforward way of showing all the alternative choices you have, as well as the time dynamic, right? So a big part of this in dealing with uncertainty and dynamic systems is the fact that uncertainty is expressed over time, and we have to incorporate that into our modeling of decision making. We also want to explicitly represent decisions and specific consequences of those decisions, and we also want to make sure we're incorporating uncertainty. So when we make a decision, the outcome is not fixed, right? So there could be upside or downside to a decision we make, and then we want to be able to capture the consequences of those decisions as well. So this slide illustrates what decision trees kind of look like, or how they're constructed at the bottom. So decision trees are like flowchart-like structures, and they're useful for understanding sort of the branching probabilities of different events happening, either as the result of a decision that you make, or just because some parameter is dynamic and uncertain. So we have 3 different types of nodes in decision trees. There are decision nodes, so we're going to represent those here by blue squares. That means we're making a decision, and based on that decision, there's uncertainty about what the outcomes are going to be, and we represent that uncertainty by different branches coming off of the decision node, and each one of those branches would be associated with a different probability of occurring. And then we have chance nodes, which are represented by these green circles. And so chance nodes can be the direct result of making a decision, and that's what's shown in the first tree. Or chance nodes can just be the direct result of a previous chance node. And so that would be sort of like describing a dynamic environmental or economic process, like electricity prices or temperatures or something like that, where in the first period, temperature is 80 degrees, and then what you're basically saying is, given the fact that the temperature is 80 degrees, there are, we're going to say, 3 main possibilities for what it is in the next period, and each of those is assigned a different probability. And then we have end nodes, which are represented by red triangles. And end nodes are a way of keeping track of, the value of whatever metric we're paying attention to as a criteria for making decision. And that could be net present value, or revenues, or cost, or some sort of environmental metric. So let's do an easy example here. And so in this example, we're pretending that we're building managers, and we already have one elevator that's in place and is mostly functional. And we're trying to figure out if we want to build more. And we are looking at the choice of building one more elevator so that we have 2, or 2 more elevators so that we have 3. And the reason we're contemplating this is because there is a probability, a 30% probability, that on any given day that our one elevator will be offline. And there's a cost associated with that we don't want to experience of $10,000. And adding more elevators reduces the probability of, on any given day, there being no elevator operational. So if we have 2 elevators in place, the probability of having no elevators operational goes down to 9%. So 30 times 30. And with 3 elevators, it drops down to 2.7%. Now there is a cost associated with expanding the number of elevators we have. If we build one more elevator, it'll cost us $40,000. If we build 2 more elevators, it'll cost us $70,000. So what we want to figure out is what's the best approach here. What choice about the number of elevators that we build leads to the smallest cost, basically. So we have a decision node, which is the blue square, and that is how many elevators we're going to have. So a single, 2 elevators, or 3 elevators. And each one of those choices goes through then a chance node. And the chance node branches out into 2 different possibilities. At the top branch of each of these chance nodes is the probability that, given the choice about the number of elevators that we pick, that those elevators experience continuous operation all the way through, right? So there's no outage at all. The bottom branch of coming out of each chance node is a situation in which all elevators fail, right? So we experience some downtime where no one can take an elevator. And so we are distinguishing both of those different branches in terms of their probability. So the probability of all elevators failing is written underneath the bottom branch. So the first one, it's P. And the probability of continuous operation is 1 minus P. Right? So we're assuming it's a zero-sum game. And in the case of continuous operation, it doesn't mean that if you have 2 or 3 elevators, that doesn't mean that all elevators are working. It just means that at least one elevator is working. And then we also have the metrics, right? So the criteria on which we're sort of evaluating this process, represented by the red triangles, the consequences of our decisions and combined with the chance nodes. So in the case of a single elevator, continuous operation leads to a cost of 0, right? So we're assuming that we already have one single elevator in place, so we don't have to build anything more. So we don't have to pay the capital cost of installing a new elevator, and there's no elevator that failed. So there's no cost per downtime associated with one single elevator that has continuous operation. The bottom branch coming out of the single elevator chance node is 0 minus the cost per day of downtime times 2. And so we're saying that in this case, that the minus cost per day of downtime times 2 would be the cost associated with that elevator failing. And we can look at sort of similar information coming out of the chance node for 2 elevators, right? There's a top branch that is associated with the probability of continuous operation as well as the cost of continuous operation, in which there's no point at which all elevators fail. So we have a minus 40,000 here because that's how much it costs us to build an extra elevator. So the minus 40,000 is sort of the best case scenario for building 2 elevators, because that means that we build 2 elevators, we have to pay for it. The extra elevator costs us 40,000, but we don't experience any downtime. Now there's a probability, of course, associated with continuous operation in this case, as is there a probability associated with the 2 elevators failing simultaneously, and we saw that that's a much smaller probability, but we have to account for that, and that's what the bottom branch coming out of the 2 elevators chance node is. And in that case, the end result, the consequence, would be minus 40,000, which is the cost of building an extra elevator, minus the cost per day of downtime times 3. And there's no, in this case, significance associated with the times 2 times 3 times 3.5. That's just part of how we set the problem up. What that's generally implying is that the cost of failure associated with with downtime for 3 elevators is more expensive than the cost of downtime associated with 1 elevator. Right? That's all we're saying, is that the consequences are more severe if you experience a failure with a simultaneous failure of more elevators. And then we can look at something similar for 3 elevators. In this case, for the continuous operation, the best case scenario is that we are paying 70,000, so that would be the cost of adding 2 elevators. And then the bottom branch here is 70,000 minus 70,000 minus the cost per day of downtime times 3.5. Now, of course, one thing to note here is that the probability of 3 elevators failing, which would be the probability of experiencing that very bottom branch, minus 70,000 minus the cost per day downtime times 3.5, is really low. It's 2.7%, right? Whereas, the cost, the probability of an all failure for 2 elevators is 9%, right? So there's a trade-off here. The consequences of all 3 elevators failing is much more severe, but the probability is also much lower as well. And so that's part of the information we have to incorporate when we're making a decision. So I mentioned at the beginning that at least, there's a lot of different ways to evaluate the outcomes of decision trees and use that to make a choice about what to do. We're going to mostly assume that we're going to do everything based on expected value. And what that means is that we want to, for each single individual decision that we make, find the expected value. And so what that means is we want to find the expected cost of having a single elevator, expected cost of 2 elevators, and expected cost of 3 elevators. And we can do that here because we have probabilities associated with each possible outcome when you build 1 elevator, or when you build 2 elevators, and when you build 3 elevators. So let's do the single elevator first. When we're talking about the expected value, what that means is cost times probability of experiencing that cost. And so remember, the cost per day of downtime we've said is 10,000. So for a single elevator, the two consequences, the two possible costs we could experience are 0 and 0 minus 10,000 times 2, or 20,000. Now the probabilities associated with those, it's a 70% chance that we have just continuous operation, and a 30% chance that if we have a single elevator, we experience a failure. Because we said that the probability of a single elevator going out is 30%. So if we only have a single elevator, the probability of having no elevators available is 30%. So to find the expected value for of the choice of just maintaining a single elevator, then becomes 0 times 0.7, so a 70% chance of continuous operation, plus a 30% chance of losing 20,000. And we can move down and do the same thing for 2 elevators. In this case, the cost associated with, the two possible costs associated with having 2 elevators are negative 40,000, and that's just the cost of building an additional elevator to get a second one, and minus 70,000, and that's minus 40,000, so the cost of building the extra elevator, minus the cost per day of downtime, which is 10,000 times 3. And that represents the cost that we would incur if we built 2 elevators and they both failed. But we have to also look at the probabilities of those 2 events occurring. So if we build 2 elevators, the probability that we at least have one operational at all times is pretty high. It's 91%. Because when the probability of having 2 elevators and them simultaneously failing is only 9%. So 0.3 times 0.3. So the expected value here is minus 40,000 times 91% plus minus 70,000 times 9%. So we add those up to find the expected value. And we could do the same thing for the third one as well. So for 3 elevators, the best case scenario is that we pay $70,000 to add two more elevators to get 3, and that they operate continuously. And there's a really high chance of them, at least one elevator being online all the time, because now we have 3. So it's minus 70 times 97.3% plus negative 105,000 times 2.7% chance. And so we get negative 105,000 by taking minus 70,000 minus the cost per day of downtime, so 10,000 times 3.5. And so here, I've sort of indicated, and you can do the math yourself if you want to figure it out, that the first choice has the lowest expected value. So we're trying to minimize the expected value here, and so the green box associated with just having one elevator is the best choice, because we have a pretty low expected value here. So the next step, if we wanted to really challenge some of the assumptions that we're making, I mean, there's a couple areas here that are worth paying attention to. The first is the assumptions that we're making about the probability of failure of a single elevator. We could be wrong about that. We're saying basically that there's a 30% chance on any given day that any single elevator fails. And so that there's a 9% chance that 2 elevators fail, and there's a 2.7% chance that 3 elevators fail. We could be wrong about that, and we would want to incorporate, do some sensitivity analysis about what happens if we're underestimating the probability of an elevator failing, or what happens if we're overestimating that probability. And we also may be wrong about the cost per day of downtime. We had said that it was 10,000. But it could be much higher than that, or it could be lower than that. And so what this is illustrating, and actually the results here don't match up with the decision tree we just did. What this is doing is it's plotting on the y-axis the per day likelihood of an elevator failure. In our case it was 30%, so we would be way up on the y-axis beyond what's shown here. And the cost per day of downtime, ours was 10,000, and so this is showing from 0 all the way up to basically 200,000. And the colors, or at least the patterns, indicate which choice is optimal, which choice has the lowest expected value. So the blue region would be combinations of per day likelihood and per day of downtime costs that would make it optimal to choose the single elevator. All the green area would be situations in which you'd want to get 2 elevators, and all the red would be 3 elevators. And so again, I'm not sure these results actually reflect the decision tree we just did, but I think the idea of this figure, this slide, is to show you that this would be an important next step in trying to make sure that the decision we come up with based on the decision tree is robust in the face of uncertainty about the general assumptions we're making about how the system works in terms of the probability of elevators failing and then associated costs when they do fail. So let's do another example. Now we are a solar developer, and we're bidding on a construction project for a larger utility. They put out an RFP in order to solicit developers for projects, and they're really we're going to compete against other developers based on project cost. And so the general rule of thumb here is that the project itself is going to cost $5.5 million to build, no matter what, and it costs us some money to put the bid together, right? To write up the report, to hire people to do, some analysis of project feasibility and stuff like that, and that's $50,000. So it costs us $50,000 to just place the bid. The project itself is going to cost us $5.5 million, and then the profit we make on that is anything above those combined costs. And so that's what our bid is, right? So we can bid nothing, and all we would lose is the cost of putting together the estimate, right? The bid. We're assuming that even if we don't bid, we're still going to pay the $50,000 to investigate whether or not we should bid. And then we're considering 4 different bid values. So $6.7 million, $7 million, $7.25 million, and $7.5 million. And so the way to think about this is the money we would potentially make would be what we bid minus $5.5 million for the project cost, minus the $50,000 for putting the report together, or doing the study about whether or not we should make a bid. And so you might think initially we should definitely just bid $7.5 million, because 7.5 minus 5.5 minus 50,000 is about $2 million. So we would make a profit of about $2 million if we bid 7.5. The problem there is that we're going to say that the probability of having the bid actually accepted decreases substantially as you increase the bid. In other words, you're much more likely to have the bid rejected if you bid a high number, $7.5 million, than if you bid a low number like $6.75 million. That would give you lower profits, but a higher likelihood that the bid is accepted. And so we're trying to figure out what bid we should make here based on the cost, the project costs, the cost of putting the bid together, which is $50,000. The potential profits which we would make, which depends on the bid value itself, as well as the probability, given what our bid is, that it's rejected or accepted. Now, if it's rejected, we don't make any money off of this, but we still have to pay the $50,000. So there's 5 different decisions we can make here. The first is no bid, and in that case we just lose $50,000. The second is that we bid $6.75 million. And in that case, there's an 80% chance of it being accepted, a 20% chance of it being rejected. If it's accepted, the money we make is $6.75 million minus the project costs of $5.5 million minus $50,000 to put the study together. If it's rejected, and there's a 20% chance of it being rejected, we lose $50,000. If we bid $7 million here, which is the third possible decision, there's a 60% chance it's accepted, and we make $7 million minus 5.5 minus 50,000. But a 40% chance that it's rejected, and then we just lose $50,000, and so forth and so on. You can go down through $7.25 and $7.5 million as well. So again, the criterion we're gonna use here to make a decision is the expected value, right? So there's uncertainty associated with each decision that we make, except for the no bid. And we need to account for that uncertainty and to take the expected value in order to assign a single value for each possible decision that we're considering here. So in the case of no bid, there's actually no uncertainty. If we decide that there's no bid, we're just going to lose $50,000. If we bid $6.7 million, we have an 80% chance of making $1.2 million and a 20% chance of losing $50,000. If we bid $7 million, we have a 60% chance of making $1.45 million and a 40% chance of losing $50,000. If we bid $7.25 million, we have a 40% chance of making $1.75 million and a 60% chance of losing $50,000. And if we bid $7.5 million, we have a 20% chance of making $1.95 million and an 80% chance of losing $50,000. So in each box, we would add the numbers together, the top and bottom branch, and sum them up to get the expected value. And in this case, the low bid of $6.75 million has the highest expected value. Okay, so now let's take it a little bit further. So we're still looking at this solar developer who's trying to figure out if it should make a bid, and if it does, how much its bid should be. And now we want to introduce some stochastic elements here. And what that means is that the probabilities of having your bid accepted or rejected in each case of a bid is not set in stone, right? Before, we were able to take the expected value pretty easily because we said, for example, the probability of having your bid accepted if you make a bid of $6.7 million is 80%, and it's 20% to get rejected. And it was a 60% chance of getting accepted if you bid $7 million, and a 40% chance of getting rejected if you bid $7 million. Here we are saying that we're not going to assume that those values are set in stone here. We're going to assume that it's stochastic, right? So our bid would be accepted in each case if the bid is lower than the lowest competing bid, right? So if it's lower than the bids of all our competitors. But it would be rejected if our bid is greater than or equal to the bids of all of our competitors, right? And we don't know up front what those probabilities are necessarily. And so we want to make that condition be stochastic. So let's say, I mean, this is closely related to what we were doing before, but let's say that now there's this other variable that actually determines whether or not our bid is accepted or rejected, and it's how our bid compares to the lowest competing bid. And instead of saying assigning, a certain probability for each bid level of our own. Let's say that there's a probability distribution defining the probability of there being a competing bid of a certain level, right? So here we have a normal or Gaussian distribution here that describes the probability of getting of somebody else, some other one of our competitors, another developer, putting forward a bid of a certain value, right? So what we're saying here is that the mean competing bid is about $7 million. And it's really unlikely that somebody else puts forward a bid that's really low, so $4.5 million, or really high, so $9.5 million. It's likely that it'll be somewhere in the 6 to 8 range. So what we can do if we have such a distribution, and coming up with this distribution could be quite challenging. You have to think about what information you would use to really put that information forward. Maybe you look at previous RFPs, like what other people put forward. There could be a number of different ways that you would try to build that probability distribution, but the idea here is that you have this decision tree, right? And you have a probability distribution describing the main source of uncertainty here, which is what everybody else is going to bid. And you could just randomly sample via Monte Carlo simulation from that probability distribution, and depending on what values you get, that is going to inform what the optimal choice is going to be, right? And so you can run the Monte Carlo simulation as many times as you want, and then see how often you get optimal choices of each kind. So what this is saying is that, for example, if we had the probability distribution that I just showed you, the Gaussian distribution showing the probability of a competing bid of a certain level, and we did like 1,000 different random samples from that, and we plugged those random samples into our decision tree, most of the time we would get that the optimal decision is to not bid. And then the rest of the time it would be pretty evenly split among the 4 different bid choices. Another way to evaluate this is to zero in on each individual choice, each individual bid decision on our part, and then to evaluate the probability of different outcomes. And so that's what this shows here. So imagine if we decided, I guess sort of before the fact, that we were going to bid $6.7 million, and we were interested in understanding all the different possible outcomes of that. We could run, a Monte Carlo simulation, 1,000 samples of 10, right? So we take 10 possible lowest competing bids, given our, the probability density function I showed you earlier. And then we take the expected value of those, and we do it 1,000 times. Well, we would end up with a histogram of expected values, basically, of potential values of a bid of $6.75 million. And what we would end up with is a distribution that shows that we're going to be profitable most of the time, where it's pretty unlikely we're going to make anything more than $1 million, pretty unlikely that we're going to experience significant losses, most likely that we make something on the order of between $200,000 and $700,000. And we can do the same thing for each bid that we make, or potential bid that we could make. So for example, we could just do the same thing, say we're going to make a bid of $7 million. What are all the possible outcomes that could happen, right? And so it's not that if you make a bid of $7 million, you're either going to lose $50,000 or make another certain amount. But what we're doing here is saying that we're going to, do Monte Carlo simulation, 1,000 times of 10 different samples, and we're taking the expected value of each of one of those samples of 10 here, and plotting that using a histogram or a density function here. Okay, so mostly what I've talked about so far is using the expected value as a decision criterion, and I want to move a little bit away from that now because it's a reasonable approach, but it's not really reflective of the full range of concerns that we might have when making a really big infrastructure decision, like building a power plant or developing a solar power farm, etc. And so, so what we've looked at so far is maximizing expected value from different choices, and going with the choice that results in the biggest mean value, right? But that doesn't tell us the whole picture, because we could have two separate decisions with the same expected value, but they could pose much different worst case scenarios. And so we have to think about not only the mean, but also the variance, or the shape of the distribution as well. So, and this gets into not behavioral economics, but utility, right? So, and whether people are, how risk averse people are, right? So if you had two different choices, and we could represent the probability of outcomes from those two different choices using probability distributions, and we said, okay, well, choice 1 is blue here, and choice 2 is red, they have the exact same expected value. So if we're thinking about things in terms of traditional, decision analysis in which we're maximizing the expected value, we wouldn't be able to discern any difference between these two choices, but they're clearly different, right? And in particular, the probability that you experience a really big loss here, so a value that's on the lower end of the x-axis, is much higher if you choose the red choice here. In other words, you have much more certainty if you go the blue direction that whatever the outcome is going to be, it's going to be pretty close to the expected value, right? So it has lower variance. And so this brings up this idea of attitudes towards risk. Now, being risk averse means that you are more afraid of the potential downside of the red distribution than you are of its upside, right? Because not only if you choose the red distribution, you have a higher probability of experiencing a really low value, but you also have a higher probability of experiencing a really high value too. That's the trade-off with choosing the more uncertain option in red. If you're risk averse, you see the tail off to the left, and you say, I care about that more than I care about the tail off to the right. And so you would prefer the blue option. You're willing to give up the potential upside in order to eliminate your potential downside. And so it's a question that's worth asking. If you are risk averse, the question is, how much would you be willing to shift the blue distribution to the left in order to accept a lower expected value, in order to shrink the variance, right? So right now they have the same expected value, but if the choice was, let's say you're at the red distribution, that's your only choice, and you had some ability to pay money to shift the whole distribution to the left in order to shrink its variance, to make it look more like the blue distribution, how much would you pay? And that value that you're willing to pay is really the risk premium, right? That's how much you would pay to gain a more certain outcome. So I think the way to think about the variance around those two distributions, right? You have two choices, they have the same expected value, but one is much more variable. I think the way to think about that is the one that has much more variability is more subject to uncertainty in the market, right? Whether that's because of changing technology, changing commodity costs or prices, increased competition, stuff like that. There are a number of forces that could create more uncertainty about the decisions you make without necessarily changing the expected value. And when we think about our desire to have more certainty, especially around choices that we make about big infrastructure related to energy, and the desire to shrink the variance around the expected value, I think there's an ability to build that into the decision-making process about infrastructure. So if we know that we would be willing to sacrifice some expected value, in other words, shift the distribution of possible outcomes to the left a little bit in exchange for shrinking the variance. In other words, we have identified some risk premium that we would pay. That can actually translate to specific decisions we make about infrastructure, and especially within the energy industry. So if all of these, if the variance around the expected value is really a reflection of uncertainty in the market, then we can think of decisions that we make about, how we build a plant, or the timeline of construction, or stuff like that. Decisions about infrastructure that give us more flexibility in responding to uncertainty in the market. We call these real options, right? And so these are ways of going about building things, like making decisions about infrastructure that give us more flexibility. And the added flexibility gives us an ability to shrink the variance around the expected value. And so there's a number of different ways you can think about real options in terms of infrastructure decisions. It could be delaying an important decision. In other words, if things look too uncertain at the moment, you wait, and you wait till you get more information about the path of different prices or costs or technologies. And that's one way of shrinking the variance around the expected value. You could make smaller incremental decisions as opposed to a single big one. Or you could pay directly for a plant that's more flexible. In other words, you could pay for one that can be used two different ways instead of just one. And all of those are ways of shrinking the variance around the expected value. But all of these are also ones that probably increase the cost or lower the expected value overall. And so what we're really thinking about here is a trade-off between a slightly lower expected value and a greater certainty or lower variance around that expected value. And that trade-off, how you make that trade-off, depends on how risk-averse you are, but there are options for doing that can be directly built into the decisions you make about the infrastructure itself. So let's look at an example from the electric power sector. So let's say a utility is trying to figure out how much additional capacity it should build, but it doesn't know what electricity demand is going to be like in the future. So it has two choices here. It can build in low capacity, or it could build high capacity. And once you make those two choices, then you have these chance variables that split up into two different possibilities. The first possibility is that the capacity that you have meets demand, and then the second possibility is that you have to pretty quickly upgrade your capacity because the capacity you have doesn't meet electricity demand. And both of those conditions are possible for each decision, right? So there's a possibility that low capacity meets demand, high capacity meets demand. There's also a possibility that you need an upgrade if you have low capacity, and there's a possibility that you need an upgrade if you have high capacity. But obviously, the probability that you need an upgrade, given the fact that you built high capacity, is much lower than the probability that you need an upgrade if you built low capacity. And here we're saying this is a stochastic tree, so we're saying that the conditions that would require you to make an upgrade depend on where electricity demand is. So if electricity demand is greater than 1200 in the instance of having low capacity, then you have to, that triggers an upgrade requirement. If electricity demand is greater than 1800, if you have high capacity, then you need an upgrade requirement. And so then we also have cost associated with each one of these outcomes, right? So we're trying to minimize the cost here of meeting electricity demand. So there's a capital cost associated with low capacity, and then there's a capital cost associated with retrofit, and then there's a capital cost associated with high capacity. And each one of these different branches from our two different chance nodes results in an end cost and then a probability of experiencing those end costs. And we're trying to figure out what the lowest expected value here is. So let's say that the low capacity capital cost is $1 billion. The high capacity capital cost is $2 billion. The retrofit cost is $1.5 billion. So that sort of reflects the fact that planning ahead and building capacity ahead of time is generally cheaper than waiting until the last minute. Maybe your financing conditions are less ideal, or you have to pay more or something like that. And then we're going to assign probabilities of electricity demand being greater than or equal to these different thresholds off to the side. So a 20% chance that demand is less than or equal to 1200, 80% chance that it's greater than 1200, 20% chance that it's greater than 1800, and 80% chance that it's less than or equal to 1800. So we want to find the lowest expected value here for each one of these, for across these two possible decisions. And so similar to what we've looked at in the past, we're going to say that we're going to calculate the expected value by summing the costs and the probabilities of each outcome for each decision. And in this case, the lowest expected value is associated with building less capacity in, right? That's what's shown in green here. And so what that suggests is that even though there's a higher likelihood of additional retrofit, and even though retrofitting is generally more expensive per megawatt of capacity, making a smaller upfront investment ends up having a lower expected value because the cost of building in high capacity from the very beginning ends up resulting in much higher system costs overall. Okay, that's the end of this lecture. Next time we're going to talk about stochastic optimization, which is going to be a continuation of our discussion of decision analysis, but a little more complicated.